This is calculus in a single variable, and I'm Robert Ghrist, professor of mathematics and electrical and systems engineering at the University of Pennsylvania. We're about to begin Lecture 1 on functions.
Here we'll review several functions that you've already encountered in mathematics before: trigonometrics, polynomials, exponentials, and we'll end the lesson with a mysterious formula.
Calculus is really all about functions. You're probably used to thinking of functions in terms of their graphs, where you plot x versus f of x. A slightly different perspective thinks of x as an input and f of x as an output. And it's not a bad idea at all to visualize a function as a machine that takes in x and returns f of x. From that perspective, certain terminologies concerning functions are clear. The collection of all possible inputs is called the domain. The collection of all possible outputs is called the range. Now, this is single variable calculus, which means that our domains and ranges are especially simple, the reals or some subinterval thereof. Certain operations on functions are critical to understand. Perhaps the most important is that of composition. The composition of two functions, f and g, is defined to be the function that takes as its input x and returns as its output g of x fed into f. That is read f of g of x. One thinks of this as first you do g, and then you plug the output of g into the input of f. Let's look at a simple example. The square root of 1 minus x squared can be thought of as the composition of two functions, f and g. If g is the function 1 minus x squared, then what would f be? F would be the function that takes an input and returns its square root. Another operation on functions that is very important is the inverse. The inverse is written f with a superscript -1. That does not mean the reciprocal of f. This denotes the inverse. The inverse is the function that undoes f. By which I mean, if you plug x into f, what output do you get? You get f of x. If you plug f of x into f inverse, what you will get is x. F inverse undoes f. Now notice that you can run this machine both ways. If you plug x into f inverse, what you get when you plug that into f is x back again. Let's look at a simple example. If we consider the function x cubed, then its inverse is going to be x to the 1/3, or rather the cube root of x. Why is that? If we take the cube root of x cubed, we get x. If we take the cube of the cube root, we get x back again. Now notice the symmetry that you see in the graphs. The graphs of f and f inverse are always going to be symmetric about the line y equals x. That is, the line where the input and the output are the same. Certain classes of functions are critical to calculus. Perhaps the simplest is that of the polynomials. A polynomial is a function of the form a constant plus a constant times x plus a constant times x squared, all the way up to a constant times x to the n for some finite n. That top power is called the degree of the polynomial. We can also write a polynomial using a summation notation. The sum, k goes from 0 to n, of constant c sub k times monomial term x to the k. That summation symbol is going to be used very frequently in this course. You might as well get used to it now. Another class of functions, very simple to work with, are the rational functions. Rational functions are functions of the form p of x over q of x, where each is a polynomial. These are very simple to work with. For example, 3x minus 1 over x squared plus x minus 6. The only thing you have to be careful of with a rational function is the denominator. When the denominator takes a value of 0, then the function may not be well defined. Other powers, besides those of positive integers, are useful. Let's review. What is x to the 0? And we all know what that is. That's equal to 1. What is x to the negative 1/2? Well, recall a fractional power denotes roots. For example, x to the 1/2 means the square root of x. The negative sign in the exponent means that we take the reciprocal. So the answer is 1 over root x. What is x to the 22/7? Well, that means we take x to the 22nd power and look at the 7th root of that. What is x to the pi? When you take an irrational power, it seems as though we ought to be able to make sense of that by some sort of limit. Well, let's keep that in the back of our heads for the moment and turn to some other matters. Let's see. The trigonometric functions are of primary importance in calculus and the rest of mathematics. You should be familiar with the basic trigonometric functions, sine and cosine. One of the things you're going to have to keep in mind and remember is that cosine squared plus sine squared equals 1. There are several ways to think about that geometrically. For example, if we look at a right triangle with hypotenuse 1, then the sine of the angle theta gives you the opposite side length. The cosine gives you the adjacent side length to that theta. We can embed that picture into a diagram for the unit circle, where we see that cosine of theta and sine of theta returns the x and y coordinates of a point on the unit circle with angle theta to the x-axis. That explains the nature of the formula cosine squared plus sine squared equals 1. It's simply the Pythagorean theorem for the x and y coordinate of that triangle. There are other trigonometric functions as well. Besides sine and cosine, you should be familiar with the tangent function, the ratio of the sine to the cosine, as well as the cotangent function, its reciprocal, cosine over sine. The secant function is the reciprocal of the cosine, and the cosecant function is the reciprocal of the sine. All four of these have vertical asymptotes at regions where the denominator term goes to 0. The inverse trigonometric functions are likewise very useful. One must be a little bit careful with these, however. One often writes sine -1 in the exponent to denote the inverse, but this can cause confusion. Students might think that this is 1 over the sine, that is the cosecant. That's a bad idea. I recommend instead using the terminology arcsine for the inverse of the sine function. The arcsine function takes on values between -π/2 and π/2 and has a restricted domain going from -1 to 1. The arccosine function likewise has a restricted domain from -1 to 1, but is chosen to take values between 0 and π. The arctangent function, unlike these two, has an unbounded domain. It is well defined for all inputs, but it has a restricted range between -π/2 and π/2. Our last class of important functions concerns the exponential. You should have seen the exponential function e to the x in your previous pre-calculus and calculus background. You know what its graph looks like. You know also its inverse, the log function, or more properly, the natural logarithm function. These are logarithms base e. These two are inverse to one another. That means their graphs are symmetric about the diagonal line y equals x. You know that, for example, e to the 0 equals 1, because anything to the 0 equals 1. Therefore, you know also that log of 1 equals 0. Now, you've seen these functions before, but if I ask you, what exactly do I mean by e? When I say log base e, or e to the x, what is meant by that? You could answer that e is the number for which the natural log of e equals 1. But then what do we mean by the natural logarithm? Well, of course, e is simply a number, a particular irrational number, a location on the real number line. But why is that number so special? Where did it come from? Why is it so useful and prevalent in mathematics? Before we answer that question, we need to go over some properties associated to the exponential function e to the x. Let's recall some of the algebraic properties first. For example, e to the x times e to the y equals e to the x plus y. In like manner, e to the x raised to the yth power equals e to the x times y. Both of these properties follow from the simple properties for exponents. E to the x, however, has some very unique properties concerning derivatives and integrals. In your previous exposure to calculus, you've seen a little bit concerning derivatives and integrals, and you may have seen the following two important examples. The derivative of e to the x equals e to the x. The integral of e to the x dx, likewise, is e to the x. Oh, plus a constant. Don't forget that. We'll be talking more about these ideas and these properties later. But for the moment, keep them in mind. We'll see them again next lecture. Now, there's one formula that ties together all of the functions that we've looked at in this first lesson: trigonometrics, exponentials, and that is Euler's formula. Euler's formula states that e to the ix equals cosine of x plus I times sine of x. You may or may not have seen this before. Let's think for a moment about what it means. It's a wonderful formula, if we can make sense of it. First of all, a little bit about the terminology used. The I in the exponent is the imaginary number square root of -1. It's the number that has the property that I squared is equal to -1. This is not a real number. That doesn't mean that it doesn't exist. It just means it is not on the real number line. Euler's formula concerns the exponentiation of an imaginary variable. What exactly does that mean? How is this related to trigonometric functions? The graphs of these two don't seem to be alike at all. That is something that we will answer in our next lesson.
Our introduction to functions is complete, but the mystery of Euler's formula remains. In our next lesson, we'll resolve that mystery by coming to a deeper understanding of what the exponential function is and does.